Have you ever wondered how electronic circuits can precisely control and magnify an incoming electrical signal, perhaps from a tiny sensor, into something much more substantial and usable? The key often lies in fundamental configurations like the inverting amplifier, which offers a reliable way to achieve this. The voltage gain of an ideal inverting amplifier is determined by the negative ratio of its feedback resistor to its input resistor. Specifically, the voltage gain, often denoted as a sub V, equals minus R sub F divided by R sub I here. R sub F is the resistance of the feedback resistor connected between the output and the inverting input, and R sub I is the resistance of the input resistor connected between the input signal and the inverting input. This elegant relationship stems from the ideal operational amplifier, or op-amp, characteristics and the application of negative feedback. An ideal op-amp has infinite input impedance, zero output impedance, and most critically, infinite open-loop gain. With negative feedback, the op-amp strives to keep the voltage difference between its inverting and non-inverting inputs at zero. Since the non-inverting input is typically grounded in an inverting amplifier, this forces the inverting input to effectively be at 0 volts, a concept we call a virtual ground. This virtual ground simplifies the circuit analysis significantly, allowing us to derive the straightforward gain formula based purely on the external resistors. To practically apply this, you simply choose your desired gain and then select the appropriate resistor values. For example, if you need a gain of -10, you could use a 10 kiloohm feedback resistor and a 1 kiloohm input resistor. You can easily adjust the gain by changing either resistor, making the inverting amplifier very flexible for different signal conditioning needs. Remember, the negative sign indicates a 180-degree phase shift between the input and output signals, meaning a positive input swing results in a negative output swing. An interesting detail about the inverting amplifier is that its input impedance is effectively equal to the input resistor, R sub I, because the inverting input acts as a virtual ground. This makes it straightforward to predict the load the amplifier places on the signal source. The output impedance, due to the op-amp's inherent characteristics and negative feedback, remains very low, which is excellent for driving subsequent stages in a circuit without significant voltage drops. Ultimately, the voltage gain of an inverting amplifier provides a highly predictable and controllable method for amplifying and inverting electrical signals. By simply selecting two resistor values, engineers gain precise command over amplification, leveraging the powerful virtual ground concept to create a stable and versatile circuit cornerstone in many electronic designs.